So before we go, and actually he's going to come, I'm just waiting for one of the student because he asked me something of, after the class. Anyway, I can start with that, and in the meanwhile, so okay, so just a very quick recap of what the things that we did yesterday. That I told you that this is the overall model of the battery system in its full glory. That means there are particles which are also known as active particles. There is electrolyte which is present everywhere, right? And there is a separator in between, right? All these things we saw, that what are the, there is a current collector, right? And then I told you that there are various ways or various level of detail by which actually you can model the battery, right? We in yesterday class we went through the micro scale modeling. Today the goal is going to be uh, covering the aspect of the homogenized model and the DFN model. These two we want to cover it today, okay? And that is the goal, and this was the overall schematic. So we will continue to use the similar symbols and notation that we have used yesterday, and this was kind of, if you put it, this is what actually we did yesterday. So these are the all the equation. Before we actually jump into this thing, I just wanted to clarify one thing, and okay, fine. Okay, so let's think about the thermal system, right? So in thermal system, the governing equation is del q by, sorry, del T by rho Cp plus del dot q equal to 0, where the q is minus k del T. This is the overall equation, right? Fine. Now if I take a particular domain where I want to solve the heat transfer problem, this thermal equation, then apart from this governing equation, what I need is, I need the boundary condition, right? So that means either on the part of the boundary I will be prescribing the temperature, which is known as Dirichlet boundary condition, or I will be prescribing the Q, the heat flux, which is known as Newman boundary condition, okay? And the thing that I wanted to highlight is, let's say for whatever reason there is a bit of heterogeneity in the domain, okay? So it is of the material 1 and this is the material 2, right? So apart from the boundary, now there is a new thing in the problem, okay? And that is the interface between the two domains, right? So apart from the boundary condition, we need what are known as interface condition. What is happening at the interface, right? So in case of thermal problem, the at the interface, the condition is the temperature that is there at the M1 domain in the boundary is going to be equal to the temperature in the M2 domain, okay? So that means that there is a continuity of the temperature field, okay? Apart from that, this is not in actually, apart from this, there is a continuity of heat flux, okay? So the continuity of the heat flux is that the Q dot N in the material domain 1 is going to be Q dot N in the material domain 2, fine, okay? So this is, so at the interface also you require some condition, right? Now apart from this condition that is there, let's say now let me make the problem slightly more complicated, okay? Now let's say there is some kind of heat source. There is a, let's say, wire that is, I inserted some kind of wire, I am flowing the current. So now there is going to be some kind of localized heating at the interface, which is going to be given by some formula like something like I square R. It doesn't matter. Ultimately, there is some kind of heat source, right? Then this continuity of the heat flux will no longer be there, okay? Then it will be like Q dot N M1 minus Q dot N M2 will be equal to the some kind of heat source that you have generated per unit area, okay? So interface, so all I am trying to connect here is apart, so for, or you also require initial condition, because if my plate is already was there at 100 degrees Celsius, the final response is going to be different. If my plate is 50 degrees Celsius, the final response is going to be different, right? So I need the initial condition, that is T at T0 at T equal to 0. Even that is required, right? So right, so in any arbitrary problem these things are required. One, initial condition, boundary condition, and third, interface condition. Okay, so now let's come to the equation and let's revise what we have done. So this is, I told you that there are two domain. One is the electrode domain, another is the electrolyte domain. In the electrode we saw that the first equation is the conservation of the lithium in the electrode particles. The second equation is a conservation of the charge again in the electrode particle, that is happening because of the flow of the electron. This one is the flux, that is given by the diffusion constant and concentration gradient. So this is how the flux and the concentration is related. The last one here is Ik equal to sigma k del phi k, where the sigma k here is the conductivity, normal electronic conductivity. Okay, fine. So these are the four things that we have in the electrode. Now in the case of electrolyte, we have the conservation of the lithium ion. The second one is conservation of the charge again. Now this flux is related with minus dc del c. There is an additional term, and this additional term is coming because I told you that in case of electrolyte there is a movement of the ions because of the electrostatic field, sorry, because of the electric field also. So that's why we have this IE, right? And T plus is the how much the positive ions are contributing to the current. Now this was the final equation where we have the current which is dependent on the electrostatic potential and the concentration, right? The one thing that you have to pay attention, this sigma is not the usual conductivity of the electronic conductivity, because in case of electrolyte the flow is happening due to the ion. So this sigma is actually the ionic conductivity, not the normal conductivity that we know. Okay, fine. Now this is fine, right? Now if I go back to the previous domain, now this was the governing equation. Now we have to take care at the interface, right? There is an interface between the electrode particle and the electrolyte, right? So if I'm not sure, I think I should use this one. So otherwise the notes will not be created. New, right? It is saved, right, or no?
This is saved, so you can close it from the top right.
Top right.
Just close the window.
Okay.
You can save it. No, in the center. In the center.
Okay. Yeah. No.
Or, yeah, no is better.
Okay.
Now, the green thing and the, yes, that opens the new file.
Fine. I think that's it. So this is a particle here, and so this is the electrode, active particle. And there is a electrolyte. Sorry, it's not. It will take some time. Right. So there is a interface now between the two domains, right? And in the interface there is a reaction that is happening, and that reaction is lithium is decomposing in the lithium plus electron. Okay, and this is the fundamental equation that is happening. The one thing to note here is this is actually not a one-way equation. Either at the positive electrode or negative electrode, the reaction is happening in both directions simultaneously, always. Whether the charging of the battery is taking place or whether the discharging of the battery is taking place, the reaction is happening in the both direction. It is never happening in a single direction. based on the condition, sometime, so this forward condition is known as uh, so this is known as reduction, sorry, oxidation. So this is forward is known as oxidation and the reversal is known as reduction, right? So this the only thing is which is dominating. Sometime oxidation will dominate, sometime the reduction will dominate based on the position and based on the charging or discharging. But both are happening at the same time, right? So the current that is overall flowing is given by J equal to J naught, right? And then we have e to the power 1 minus beta f eta r t minus e to the power minus beta f eta upon r t. Okay, fine. So this is the current per unit area at the interface. Okay, now this is, if it is positive, okay, that means the current is flowing from the electrode to electrolyte, right? Or I can just E, and this is either P or K, sorry, P or N. Okay, so if it is current is positive, means uh, the current is flowing out of the active particles. Okay, and if it is negative, that means the current is inward, right? So here also, as I told you, there are both the things are happening, right? So one of this is the oxidation current. The first term I naught into the first term implies oxidation current, and this one implies the reduction current. Okay, so this is the oxidation part, and another one is the reduction part, right? So it depends which one is dominating, right? Now beta is just some kind of constant. Typical, most of the cases you will see the beta value is taken as 0.5. That is quite a standard, unless until very rarely you will see some other value that is being taken. The F is a Faraday constant. Okay, so F is a Faraday constant, and the eta is known as over potential. Okay, so the over potential is phi k minus phi e minus open circuit voltage of that particular electrode at that particular concentration, right? Fine. Okay, now one more thing is, this reaction in general, or actually any chemical reaction, is governed by what is known as chemical potential. Okay, so chemical potential, if you know, is a quantity which is related to the Gibbs free energy. So if I take the derivative of the, so it's a Gibbs free energy per unit mole. Okay, the chemical potential, because some of you might be from the thermal background, so you can relate the chemical potential easily with the Gibbs free energy, right? Now any chemical reaction will take place, so for you can calculate this chemical potential for any chemical species. Okay, so now a general, let's say the chemical reaction is A plus B C plus D. Okay, so they are some kind of reactants in a chemical reaction. You can calculate the chemical potential of A, you can calculate the chemical potential of B, and you can add it up, right? So you can calculate the total chemical potential of these two things. You can calculate the chemical potential of these two things, right? Only if the chemical potential of the product is going to be less than the chemical potential of the reactant, then only the reaction is going to go in a forward direction. Okay, so the chemical potential plays a crucial role, like in mechanical engineering, like most of you are from I think from the mechanical engineering or the physics domain. So in general we say, right, that the system is trying to minimize its energy, right? That is the general principle we use. In thermodynamics we say that it is trying to minimize the overall free energy or gives free energy, right? So here also the reactant actually will try to, the chemical reaction actually is moving in the direction where the chemical potential of the overall system is actually kind of decreasing, right? Now why I am telling you this is because the chemical potential, the total chemical potential is actually mu naught R T ln concentration. Okay, sometimes people write it by divided by the C ref, anyway that is fine, plus Z charge number into F into phi. Okay, fine. So this is known as in general electrochemical potential. Okay, why electrochemical potential? Because of this final term. Okay, so the Z, the small z is the charge, right? For example, Li plus, for that the charge number is going to be 1. Like in case of Pf6 minus, again the charge number is going to be 1, sorry, minus 1. In case of electron it is going to be minus 1, right? So and F is the Faraday constant, again phi is the electric potential, right? So what you can see from this relationship is the overall electrochemical potential of a particular species is going to be strongly affected by the potential, right? And this, so this tells you that actually by controlling the potential you can change, you can control the this particular reaction whether it is going to be moving in the, so if you see this one, right, this is not going to get affected because the charge here is 0. This has a positive charge, so Z equal to 1. So the lithium plus ion chemical potential, electrochemical potential is going to get affected if you change the potential, right? And electron potential, chemical potential is also going to get affected once you change the potential, right? So you can actually change the potential, right, by changing the electrochemical potential by changing the overall phi, and that's why you can control whether you want the direction in the forward or in the backward, right? So this plays a very crucial role, right? So that's why when we have to charge the battery, we flip it. The positive electrode we put the negative potential, and now it is actually when we are putting the negative potential, then the phi is becoming negative, Z is negative, and then the electron potential is going overall up. Like value of the phi for the electron is, sorry, value of the mu for the electron is going up. Okay, fine. So so this actually gives a lot of intuition. I'm not going into too much detail, but this is a very important relationship if you want to understand or from the electrochemical point of view, the better, right? And the same thing is reflected in this equation, right? That the overall current is given by this over is actually significantly controlled by this over potential, right? So this is phi k, and this is phi e. Phi you are not directly controlling, but phi k more or less you are directly controlling, and open voltage is anyway more or less given to you, fine. And J naught anyway the expression is there in the slide, right? Okay, so this is what is happening at the interface. Now we have, so the I k dot nk at the interface, right, is equal to the J that I just wrote, because that is happening at the interface. So there is a current which is actually flowing out of the particle, that's why it is there, right? So this is there on the boundary of the gamma on the k, okay, and the reverse thing happened there in the electrolyte. I e dot n e equal to minus j, okay, fine. The reverse thing is happening because there the current is actually uh, going to be like, so the particle, the current is going out, so that's why it's positive for the active particle, but for the electrolyte it is going in, so that's why it is a negative sign, right? So this is the interface condition for the current or the charge conservation equation, right? Now but you have another equation, and that is the mass flux equation. So that's why if you want to calculate the mass flux, then all what you have to do is you have to divide the current by the Faraday constant. So everywhere actually you will keep on seeing Faraday constant appear, because it is actually able to relate the concentration of the species or the flux of the species to the charge, right? And then this is going to be equal to Nk dot, again small n, k, and this is again in the electrode, and you have right. So these are the interface condition, fine. Apart from that, you have the boundary condition. So boundary condition I will not touch too much upon, but the only thing I will tell that these boundaries that are there, which are at the top, at the bottom, the current that is flowing out is also 0, and the mass flux is also flowing out is a 0. So at this boundary it is going to be I tilde k dot nk equal to 0, and k tilde dot nk also going to be 0. The same way it is going to be here for the electrolyte, which is going to be I tilde E dot n E equal to 0, and the n E tilde dot E, right? Because there is nothing is coming out at the bottom, at the top. Fine. Okay. Nk is the normal to the domain. Okay. You are only computing the, like in this case, right? You have the condition on the q dot n, where the n is the normal. Here also the n is the last thing we can discuss is on the potential, the boundary condition, because you have another variable to solve apart from the concentration, that is the potential, right? So the boundary condition is so what will be the boundary condition? So let's say this is positive electrode and this is negative electrode. Sorry, this is negative electrode. So what will be the phi value here? Whatever you are prescribing, right? So especially, so that will be like P equal to 4.2 volt if it is a potential driven problem, right? If it is a charge driven problem, then rather than being prescribing the potential, you will prescribe the current. So then you will prescribe the total current that is actually at this boundary is going to be del phi dot n, and then you will multiply with the sigma E, right? And that is you are going to integrate over the whole domain, right? And this you will actually will be equal to the applied, okay, okay, I applied, okay. So that you take the del phi dot n and take the current at each point, integrate the total current, and that should be equal to the applied current, right? Apart from that, it is slightly tricky. This will not be enough if you can understand, if you know the theory slightly well. It has to be at the same potential. So it is at the same potential, and but the potential value is not known, the current value is known. And here on the other end, it is very simple. You just take the phi equal to 0. Right? Now, in terms of initial condition, you prescribed the concentration value Ck equal to Ck naught at t equal to 0, and similarly Ce equal to Ce naught. Okay. Will we need initial condition on the phi? On phi, do we need the initial condition? So these are the equation, right? So do we need the initial condition on the phi? So this equation and this equation, are they same or fundamentally same, or they are different? There is a difference, right? This one has a time derivative. So this is the transient PD. So you need the initial condition in terms of the concentration. But this is not a transient equation, right? So there is no time derivative there. So you don't need the initial condition for the phi. You only need the initial condition for the C. Okay. Fine. So this now complete the discussion on the micro scale part. Now let's move on to the homogenization. Okay. So Dr. Jain was telling me that he has covered little bit on the homogenization on the thermal part, but let's quickly go through, and if maybe in 2-3 minutes, and then we can move on to the battery part, right? So in general, what is homogenization? Do you, hopefully you understand it. So let me just repeat the argument on the homogenization. That maybe I give you one strip which looks, so for example, if I see this mobile cover, right, on the top of, if I just see from the naked eyes, it looks homogeneous in nature, right? It looks like things are uniform with respect to the spatial length. Me, if I take the material composition at this point, it looks more or less same, right? It looks like there is no difference, things are uniform, right? But maybe if you zoom out, so if you take a point in the domain and you zoom out there, actually you may see it is actually made of the different combination of the material. It's just that you are not able to see it. Okay. In case of thermal field, we do use what is known as composite kind of material. For example, you know that PCM, phase change material, has a lot of good energy storage capacity, but they are poor conductor of the heat. So a lot of time we use what is known as metal PCM composite. That means you have the metal along with the PCM, right? So for example, you may have some kind of metallic fins, and overall other place you can have the phase change material. So this is now the material is actually combination of the two, right? But when I want to analyze this system, then let's say I want to uh, understand that if I apply some temperature difference T2 T1, how much the heat is going to flow, then I know that the heat flow is minus K dt by dx, right? So, but what should be the K? What? Because at some point it is K1, some point it is K2, some point it is K3. I don't want to deal with the microstructure detail. I don't have the computational resources that I can resolve each of these things, right? So what I want to do is, I want to replace all this with a homogeneous system, right? I want to work with the that, right? So let's go to the nodes and maybe, right? So I have K1, K2, K3 and so on, and I want to replace this with the uniform K effective, if you want to call it. So this is homogenization. So the homogenization, if I simply define, it is converting a heterogeneous domain, which is actually heterogeneous, into a homogeneous domain. That is what is homogenization. It can be in a structural problem, it can be in thermal problem, it can be in fluid problem, right? But this is what the homogenization in any field. Okay. So do you know how to drive the K effective? No, so how do we drive it? So you are on a right track, but I want a slightly better steps, exact step that I can write and give the answer. Hmm? Okay. So if I will assume that there is a Q that is flowing in the system, right? And Q is going to be same in all the blocks, whether K1, K1, K2 block, K3 block, K4 block, right? The heat cannot, like whatever is the heat, because right now we are assuming the steady state, right? So whatever the heat that is coming in has to go out, right? So then the Q is minus K1. So this is, let's say, T1, this is T2, and this total length is delta x. So then it is going to be T2 minus T1 by delta x. If I do the same thing for the second domain, then the Q is going to be minus K2 T3 minus T2 by delta x, right? Clear, right? And what I can do is I can take this K1 from here to here, so Q upon K1, K2 from here to here to Q upon K2, and then I can add all these things up. So then it is going to be Q 1 upon K1 plus 1 upon K2. There will be lot of cancellation, T2 will cancel like this. So let's say the final one is T10, so then it will become T10 minus T1 divided by delta x. Okay, so the Q is going to be T10 minus T1 length. Okay, so the length is, I assume, the 10 block, so it is going to be delta x into 10, right? So length L and 10 here, and that is going to be 1 upon K1, 1 upon K10. Okay, so the effective conductivity is going to be 1 upon 0.1 upon K1 plus 0.1 upon K2, 0.1 upon K10, right? It is a very simple derivation and you can drive the effective conductivity, right? It is a very simple arrangement, that's why you are able to drive it. In case of complicated arrangement, there are special computational technique. The homogenization is a field in it itself. Okay, so one of the PhD student is doing with me working on the homogenization, but we are working on the structural aspect, not on the thermal aspect there. But so it's actually quite mathematically involved field, but anyway, we will not go into those things. But at least the central idea of the homogenization hopefully is clear, that I want to convert a heterogeneous domain into a homogeneous domain, right? And at least for simple system, I can drive the effective properties very easily, right? But if I give you a complicated system like this, I give you that this is the underlying system, this has the conductivity K2 and this has the conductivity K1, it is not that easy, right? Then you have to do the computational homogenization. You can make RV and all those things, anyway I will not go into those things. So that, yes.
So in my research seminar, I will talk about exactly this problem, where you have multiple inclusions of different properties compared to the background, and how do you solve such problems analytically?
Okay, good. Not numerically. Okay, so I know the things numerically, but it will be good to see the things how to solve it analytically. Okay, so I think after Dr. Jain lecture, you will become, it will you will become to know, you will come to know much more about this. Okay, fine, good, fine. So let's move on to our battery stuff, right? So for those who are working even remotely on the mathematical stuff or other things, I always say, at least to Kulbhushan, do not assume the things are in series or parallel or whatever it is. Always drive it. Even now I drive it, right? So I am saying even if you know the final answer, keep on, it takes 3-4 minutes of effort. But if you keep on doing this kind of exercise, things remain with you. Otherwise, you become out of touch very quickly. Right? Otherwise, you just lose the gist of the main concept, and all you remember is some formula. Right? So always, at least for some simple things, start from the basics and drive the things on your own. That helps in overall thinking. Okay. So everything is there in the book or on the web, on the Google or in the Chat GPT, right? But in order for these things to go inside your head, you have to work these things over and over and over again. Then only you can actually use them in your research effectively. Right? So now this is, now if you see this picture, it has completely changed. Rather than this beautifully looking electrode, now it's a boring uniform picture, right? Because there is a homogenization of the domain that is carried out. I am not no longer trying to resolve the heterogeneities at the micro scale and carrying out the things, right? So how do we carry out the homogenization? Actually, for homogenization, at least for whatever we are going to cover, it's a fairly simple thing, but still we need to do that. So let's do that. Okay. But at least this picture is clear, right? What we are doing, we are replacing all this heterogeneity with the homogeneous domain. Okay. So again, we'll do the same way that we have done for the microscopic model. What we will do is we start with the electrode and we'll move to the electrolyte. Right? Again, we have the 4 species to take care: lithium and electron in the electrode, and the lithium plus ion, and the charge or the anion in the electrolyte. The same 4 things we'll take care and we'll solve it. Okay. So let's do that. And good. So yes. So let's first work with the lithium in electrode particles. Now the funny thing is, after talking about all the things about the homogenization, you cannot do the homogenization for lithium movement in the battery. Okay, that is not possible, because the lithium diffusion is actually happening at the micro scale. Okay, so what is happening here when I am converting this K1, K2, K3, right, into this homogenized field? That is fine. I am actually simplifying my problem, right? But I am losing some detail. If someone want to know that how the temperature is actually varying in these interfaces at the K1, K2 boundary, I cannot tell. Right? I have lost this kind of detail that is no longer available with me. So if there is some phenomena which is happening at this length scale, and if I carry out the homogenization, you cannot expect me to find the answer for that particular phenomena. That is not possible, right? So the lithium diffusion is actually happening at the particle length scale. So we cannot do the homogenization for the lithium movement, right? So there we will stick to our normal equation, and that was del Ck over del T plus divergence of the Nk equal to 0. Here I will write in the subscript capital X, and the reason I am writing the capital X is to tell this capital X is to denote that things are happening at the micro scale or at particle level. Fine. Okay. So for each of those particle, you are still solving this equation. Okay. But only this equation, the rest of the things we will do the homogenization. Only one equation we actually keep it as it is. Okay, so I will go to the slide. Right. So this is for the electrode modeling slide. So if you see this first equation, you see the capital X, right? That is because I am actually sticking to the micro length scale. This is the overall domain, how I will solve this equation. So these are electrode particles. The black things are additive particles which are not playing any role, right? So, and the white thing is the electrolyte. Right? So if I am solving this particle, right, all this is the boundary, right? So on the boundary there can be three things, right? So ultimately to solve any equation, I told you, you require boundary condition. So here on the particle there can be three things can occur. One, there may be electrolyte that is present. That is one of the things that can happen. The second thing is additive particle may be present. That is the second thing that can happen. Another thing can happen, it is a part of this boundary, the domain that I have taken. These are the only three possibilities, right? Either at the boundary you will have the electrolyte, you will have the additive particles. Third, you are going to have a boundary of the domain, because I am taking at a time, I am just taking some small domain, right? Fine. Okay, is clear? Right. So now, right. So in case of additive material, these are inactive material. They don't do anything. They don't lay. You can, lithium is not going inside this, right? So lithium is not going inside it. That means where is there this additive material? The flux is actually equal to 0, right? Nothing is going out. They are just as there as a glue. They are not doing anything. So that's why the flux is 0. The other thing that is there, that is similar to the previous one, that the flux is equal to the current divided by the Faraday constant, right? So n tilde dot nk equal to the jk, the current that we just saw, Butler-Warmer equation, divided by the Faraday constant, that will give you the flux. And on this boundary, because these are not actually domain actual boundaries, these are only some portion of the domain that you have taken. Actually the overall electrode is much bigger, right? So these are artificial boundary that you have taken for the computation, right? So in this boundary what you do is you actually take the periodic boundary condition. So to denote that this is actually a much part of a much bigger domain, I will not go into too much detail of the periodic boundary condition, but the periodic boundary condition means whatever is happening at the top edge is happening at the bottom edge, whatever is happening on the left edge is happening on the right edge. So whatever is the concentration of the top edge is happening at the bottom, the top edge, and the, so if I take this point, the concentration here is going to be same as the concentration here. The concentration here is going to be same as the concentration here. The concentration here is going to be same as the mirror image version of that on the right hand side. Is it clear? Right? So these are known as periodic boundary condition. Again, the periodic boundary condition are not used heavily in homogenization field, whether it is a thermal homogenization or it is in the structural homogenization or whichever kind of homogenization it is. Okay, fine. So this is the, these equation are known as particle equation because you are solving now at the particle levels. Earlier we don't need to give them a special name because everything is happening, we are resolving at the micro scale, but now we are working at a different scale. So here we add the disclaimer that these equations are solved at the particle level, and that's why we are calling them as a particle equation. Fine. Okay. Geometry. Hmm. Hmm. No, so if you know, if you have this diagram, you can always generate the mesh, right? The main thing is how do you get the actual image of the electrode. That is very difficult. So I think they do some kind of, if I am not very sure, but I think X-ray tomography or something they do. There are some experimental technique which can actually look into the electrode and actually can give you the size distribution, overall size distribution, that how what is the overall. So generally you get the overall size distribution, and from that you try to model it. You don't know, actually you don't try to actually take every particles exactly how it is there in the actual battery. Even if you are trying to model the things in a great detail, what you do is you actually do some kind of experimental observation through this X-ray tomography and other things. You get what is the overall size distribution, and then you try use some computational technique which will randomly generate the particle following that particular size distribution, and then you do the model. Okay, fine. So this can you take this? Manshu ji can. अच्छा तुम्हारा तो ठीक. Thanks. Is it clear? Any other doubt? Okay. Now in the electrolyte we are going to do the things. Or yes. Actually we can do the charge conservation here. So the charge conservation is going to be simply del dot I equal to no, that is not going to be there. 1 second. Let me do that way only. We can do that. Yeah. Or we can, okay, just let me look at the notation. The same notation. So BJ I am taking. Fine. So this is, so have I modified this equation? So now this is the homogenized version of the equation. You see something has changed, right? What has changed? Earlier on the right hand side I had 0. Now I have some non-zero term, that is the known as source term. Right? So what I am doing is कि whatever is happening, so the current is generated at the interface. Right? What I am doing, I am replacing this with a homogeneous field, right? And this J which was there at the boundary, I am saying I am not taking care of the boundary. Now I am distributing the overall current in the domain, and I am simply calling this as a J. Okay. So I am converting the boundary information into a overall volumetric thing. If you are confused with the current, the best way is to try to connect the things with the thermal. Okay. So consider the case where there would have been some kind of heat source. So some kind of heat is getting generated and only at the boundary, and I want to solve this problem. Okay. So what I will do, but I don't want to resolve these boundaries and everything. I want the fairly approximate result. That is fine with me. So what I will do, I will calculate the total heat that is generated, right? And I say that, so the total heat generated, let's say is Q, right? Then what I will do, I say that I will divide this with the total volume of the domain, and this I will use as a heat source. I will assume now, in actual the heat is generating only at the interface, but I would say I don't want to resolve the interface, so I will assume that uniformly the heat is generated in this way, right? So this thing I convert the boundary thing, which is the area thing, into the volumetric thing by considering as a source term. Now the domain is homogeneous. Okay, and the I now is given by minus sigma, but this is actually homogeneous quantity into del phi So this conductivity is different from the usual conductivity, because now this is a homogenized conductivity, because the domain is consist of the electrode particle. It is also made of the binders, which has a very poor conductivity, right? So now combining all these things, I will find through either experiment, through some analytical technique, or from the numerical technique, the effective conductivity, and then I will put this into this equation. So this is not of a specific material, this is the overall effective conductivity, right? And now this boundary term has been changed to the this one, to the volumetric thing, right? So now let me show you the equation, and if I miss something I can do this way. So this is electrolyte domain. Okay, I thought I have done. Okay, right? So this is Ik equal to minus sigma k del phi k. Again, just repeating this j. If you see this expression, what I am doing, I am calculating, integrating it over all the part that is actually in touch with the electrolyte, because there only the current is flowing, and then dividing with the total area, boundary area of the particles. This will give me the j of k, and this b that I have, that is the percentage of the places where I have this boundary. Of the total boundary, how much of the percentage is the boundary between the electrode and electrolyte. Okay, fine. Because this I am computing it everywhere, right? So that's why I have to divide by that then. Okay. Fine. So now moving on to the next one. Okay. Okay. So the electrolyte, again we have will again do the homogenization, right? Now there is a one thing, there is going to be small difference compared to the previous one. So the overall domain is a heterogeneous domain. Only the part of it is occupied by the electrolyte, right? Let's say the fraction of the part or the porosity of this is epsilon. Okay, only the some part of it is actually carried out by the electrolyte, right? If I take, now I want to do the conservation of the lithium plus ion, right? So when I am taking my domain for the conservation, right, then what will be the total amount of the lithium plus ion? We saw that, right? The this is going to be C lithium plus ion that we saw in yesterday, plus, and then we have to integrate, right? But then this is the total volume, right? But I don't have the total volume available for the lithium plus ion. I have only the fractional part of it available to that, right? So if the porosity is phi, the actual part that is available is only phi into dV, right? If the porosity is 50%, only the 50% can be occupied by the electrolyte, right? Otherwise it is not going to be there. So to account for that, I put the epsilon there, and then again the same thing, del by del T, and that is going to be equal to the minus of the flux, and that is going to be the N lithium plus ion, and dot N equal to ds, right? Again I do the same thing, apply the Gauss divergence theorem and everything. I get the equation which is going to be epsilon del C Li plus by del T plus divergence of N Li plus equal to 0, right? This is if there is no source term, right? Without source term. Right? But we have the source term, right? Because there is a flux of the Li plus that is there. Earlier when we were modeling the micro thing, we wanted to resolve the interface. That's why we didn't took it as a source term. But now we don't want to do that, right? So the source term is going to be again Bx, which is same as previous. The source term is similar, again J, that we have calculated J average, and then divided by the Faraday constant, because again we want the number of moles, not the charge, right? So again the similar kind of thing. So now if you see, this is epsilon del C over del T, divergence of the flux, and now this is the source term, which is B into J divided by F, right? And in case of current, there is no F, otherwise the source term is same. And then these are anyway boundary condition, will come to that later. These two equation is same as yes micro scale. The constitutive equation is same as micro scale. Again the similar thing. This dE and sigma E are no longer the diffusion coefficient of the electrolyte or the conductivity of the electrolyte. This is again the homogenized property, because you have done the homogenization, right? There are hindrance, right? If for example, 1 second, this is the electrolyte. I have the lithium ion plus here. It want to move and go to here. It cannot directly move. It has to go and take a very tortoise path and go there. So the resistance to its movement has been significantly altered, right? So that's why these properties, the diffusion coefficient, the conductivity, everything is an effective conductivity, effective diffusion coefficient. They are not specific a particular material property. These are homogenized property now. Okay, fine. So now in case of homogenized, if we summarize the things, in case of lithium movement, things remain as it is, because we have not done any homogenization. For other things, there is a homogenization that has happened. What it has done is, it has converted the area terms into the source term, and these kind of source terms are appearing now into the equation. So because now these have become into the volumetric quantity, and apart from that, all the properties such as the diffusion coefficient, conductivity, they have been converted into the effective properties rather than being a specific property of a specific material. So this is kind of in a very broad sense the summary. Now this excellence, I told you electrolyte is everywhere. So if this electrolyte is in the negative electrode, then you will take the excellence to be the porosity of the negative electrode. If this electrolyte is in the separator, you will take the porosity of the separator. If this electrolyte is in the positive electrode, you will take the porosity of the positive electrode, right? Now same thing with the B. Sorry, this keep on happening, right? Same thing with the B. Now you see this one, Jn, which is the current density in the negative electrode and in the positive electrode. What should be the value in the separator? 0, because there is no current that is getting generated, there is no active particle there, so that is going to be simply 0. So the equation is, now it is a uniform equation where the electrolyte you are solving of whole battery, positive electrode, negative electrode, and the separator part. The only thing is, the coefficient that are appearing in the equation is different for the different domain.
The terms Jn and Jp,
do
they come from the equations in the electrodes?
Yes, they are coming from the Butler-Warmer equation.
So
that does.
Is obviously coupled with each other.
Yes, yes, and that is actually, if you see, just on this point, if you see in the numerical community of any literature in general, at least 50% of the paper, if you go to the core computational community, 50% of the paper will be where people have written their in-house code. Okay, battery literature is the only literature, at least in my limited career, I have found where most of the people uses console. They don't try to write their own code. Okay, the reason can be it is really difficult if you if someone is from the computational background and try to imagine they have to write the code. There are particles. For each of these particle, you are solving the PD, right? And now there is an electrolyte equation that you are solving at the homogeneous domain, and each of these particle equations are coupled with this one, right? And all these are non-linear PD. These are not even linear PDs, right? They have, and the J is given with something which has an exponential term, and the potential is coming in the as a power of the exponent, right? It's a highly non-linear PD, and now you're solving everything together. It becomes really at two different length scale. So as a understanding it is fairly still, I would say, compared to, I would say, implementation is still simple. If someone has to really implement and start from the scratch, it is really an exercise itself. It will take, I think, 1 to 1.5 years.
So I was actually thinking of trying to solve such problems analytically.
Okay,
I
I
was saying that even the numerical implementation is so challenging.
uh,
Solving these analytically is probably near impossible.
yes. So there is a only one paper I found. I think where they do lot of linearization. So
Yes.
so they do the linearization. They have converted the system into the linear form, and they have taken lot of assumption. I can share the paper with you. Huh. So they have what they have done. It's a paper is in that very different direction. They want to find out the transfer function of the overall domain. So they have done a lot of assumption. They have taken that the Butler-Warmer equation. Also, they have done some. I have not understood all the details, but they have linearized all the system, and they are able to drive the overall transfer function in terms of this diffusion coefficient and all those things. So they have given the nice closed form expression at the end of the paper, and they have actually given the assumption, at least the result they are showing and the validation they are showing, that is actually fairly decent.
The main non-linearity in this problem comes from the Butler-Warmer.
Yes, yes, yes.
Apart from that, the equations themselves are fairly linear.
Yes, only the length scale is different. And the one is at the micro scale and another is the macro scale. Otherwise, non-linearity as such is not there. I think there can be, this one is slightly non-linear because the mu is dependent on the log of the C. But again, maybe you can linearize at least in the small concentration you assume, and you can linearize this term. Should not be that difficult. Linearization you can do, but actually it's a non-linear term. But you can then think. But the main thing is the Butler-Warmer equation. That is the main nasty thing. So I will share you the paper, and maybe if it helps, right? I don't know. This is annoying a bit. Fine. So this is the equation that we've solved. And in terms of the boundary condition, if you see the flux is 0. So I will go back to this one. So even if you don't, if you have not understood the mathematical part of it, that is fine. But the, if you see intuitively, the main part is, if you want to drive later the boundary condition for yourself, the main thing is when the current is flowing at the current collector, all the current is flowing through the active particle only. No current is passing from the electrolyte to the current collector. That is the one thing that you have to remember. If you remember this thing, then you can write the boundary condition yourself, right? So that's why if I am in the electrolyte domain, then the del phi dot n is going to be 0, right? Sigma del phi dot n is going to be 0 because there is no current that is flowing out from the electrolyte. The same thing happened at this boundary, right? Once you understand this particular thing, then it is fine. So once you understand at each point in the domain which is contributing to the current, are the electrode is carrying the current or the electrolyte is carrying the current. So if you see this boundary, right, all the current is carried at this boundary by the electrolyte, right? Electrode particle job is done before this boundary. So from here the current is carried by the electrode also at the electrolyte also. Here till here. So here electrode is 100%. Slowly electrolyte is 100%. Till here electrolyte is 100%, and slowly electrolyte reduces, and it becomes 0 here. Okay. Once you understand that, then you can always write it. But that is the main thing that you have to understand, that which one is carrying the current where. Then it is fairly okay. Fine. So I think we are done with the homogeneous model also. Right. Now we will go to the last one, which is at the end of the day nobody, in I think 99% of the people, or even 99% probably will be underestimation. Don't use micro scale model or the homogeneous model. They use what is known as P2D model. But in order to arrive at the P2D model, you should know all these things. But at the end of the day, generally we use the P2D model. Okay. So again, so what is the P2D model? Okay. So what it is doing, it is making lot of assumption about the nature of the battery. Okay. So this model assume first of all that all the electrode particles which were having earlier funny looking shape are no longer funny. Now they are boring spherical object. Okay, the nice spherical object. All of the particles have the same size. So things have become much less interesting because things are uniform. So at least for a person who is working in the numerics, it becomes a bit boring. But yes, but it becomes much more doable. Okay. So and you assume that this, if you see this earlier I was showing you 2D domain, right? Now it has become 1D. Right? So you are assuming that the things are uniform along the y and along the z. Anyway, we have never considered. So along the y now the things are uniform. So it's like this row is getting repeated uniformly at the top. Right? So now the things have become 1D. There is nothing is moving. The current is not flowing in the y direction. Everything is only flowing in the x direction. It has now become a unidirectional case. And the particle has become uniform. Rn is the size of the negative electrode and Rp is the size of the positive electrode. Right? So the problem has simplified lot. And why the problem has simplified? Because earlier for the battery either I was solving a 2D problem or 3D problem. Now I will be solving only 1D problem, which is computationally much cheaper compared to the 2D or 3D counterpart. Right? And the particle also has become now is spherical. Right? So rather than here in case of particle also, so I think Dr. Jain mentioned today one problem, right, where he was showing the conservation of the heat in the radial coordinate, right, in the cylindrical coordinate. So the same thing you can do here, right? So you can go to the polar coordinate and work out the things there. Fine, and so I guess so I will reduce my effort little bit. So these are the particle equation. Now you see only the derivative is appearing is the r, because things are only changing as a function of the radius. Now there is no longer x and y, so it becomes nice. Only independent variable that I have is the r, which are much easier to solve. It is still two variable r and t, but at least in the spatial coordinate I have to deal with only r. So this is the particle equation it becomes. So it is a similar thing, only the grade is getting replaced by the del C over del R in some way, nothing much. And if you see the electrolyte equation, earlier I was having the grade of phi, gradient of the phi. Now it has become only del C minus del C over del X. Right? So it has become much simpler. Right? And otherwise fundamentally it is same. Right? The condition also I can write boundary condition only out of one point, because in the 1D the boundary is a point. Right? So boundary condition also become very simple. The on x equal to 0, phi n equal to 0, and all these things. So at x equal to 0, phi become equal to 0. In equal to 0 at x equal to ln. So as I told that at x equal to ln, all the current is actually taken care by the electrolyte, so the electrode will not carry any current, right? So that's why In is the current carried by the negative electrode, right? So that becomes 0. The same thing on the positive side. So now these are the equations which are much simpler compared to the LN. But in order to understand P2D model properly, you have to start with a micro scale model, then you go to the homogenization, and then you make some assumption about the nature of the particles, and once mainly you are assuming all the particle to be uniform of the spherical size, and then you are done, right? Fine. So this, there are two names to this. One is DFN model. I don't remember the full form of DFN. That is the name of three scientists who actually developed this model. The last one I know, there is a Newman. Okay, this is, he has done phenomenal work in the lithium ion battery. His papers are, I think, around 1980, if I am not wrong. Those are like still the landmark paper. All of the battery computational community will refer his paper only, right? And P2D model is pseudo 2D model, because it's not actually 1D, because it's not only X, you are solving in X as well as in the R, but it's not 2D actually, because R and X are not actually strongly coupled. It's not like X and Y. So that's why it's known as pseudo 2D model. Okay, fine. So it's, sometimes people call it 1.5D model, whatever. Okay. So what is the time and what is? Okay, I was saying I will leave early. हाँ. Okay. Okay. Fine. So I will just take 5 minutes. So this is taken from the literature only, but I think Kulbhushan did some of this analysis himself. So I just want to show some of the output so that you get feel that after doing all this work, what kind of plot we generate. Okay. So this anyway we know. So now I just kept this thing, that how many parameters you need to run the simple P2D model. Okay, it's just the last one was so simplest I didn't give more than 5 minutes. But if you have to run it, this is 15 parameter, another parameter 38 roughly, and these number of parameter you need. And if you are working in the battery modeling, one of the biggest challenges to find a paper which lists down all these 38 parameter in a proper detail.
For the chemistry that you are working on.
Yes, they don't know. They will show the validation with the experiment. They will list 30 parameter, but somehow they will always miss 4 or 5 parameter. Now it is it becomes a challenge to reproduce their result, because you are keep on figuring out what those 4 or 5 parameter they have taken.
Yeah.
And I think at least Kulbhushan has spent around 5 to 6 months figuring out those parameter itself, and so we keep on trying to model, and then we give away, okay, now this paper cannot be reproduced, now let's move to another paper who has given this 38 parameter, because even if 1 or 2 parameters are given, it becomes very difficult to actually reproduce their result. While Newman, the first guy who did it, you see their paper, his paper is phenomenal, very nicely written, everything is there in a proper detail, right? Now cherry on the top, this conductivity of the electrolyte is a function of the concentration of the ions. So you don't need only a number, you need this whole expression with lot of unknown constant to determine, or you can take it from the literature. This open circuit voltage is also a function of state of the charge of each of this electrode. Again, those data is available in the experiment, from the experiment in the literature. You can refer to that, but I just want to show this like that. It is a humongous task to actually really exactly nail down the even the P2D model. This This is known as Bergman relationship. So effective properties are function of directly the porosity. So you don't need to carry out the homogenization everything. You can just simplify this, the effective properties porosity to the power 1.5 into the actual conductivity. Okay, I will not go into detail, but if you don't want to take the trouble of homogenization or something, these are simple empirical relationship which works to a decent degree. And right, these are, so he has taken lithium, I think graphite as a negative electrode, and this magnesium oxide as the cathode, and this is showing the open circuit voltage as a function of the SOC, that how it is not constant. When it is actually fully charged, then it's a 4.2. So here it is SOC equal to 0 at the negative electrode, sorry, at the positive electrode. At the negative electrode it is SOC equal to 1, so it is going to be here the open circuit potential is going to be 0, right? So then, because the open circuit potential of the battery is positive charge open circuit voltage minus the open circuit voltage of the negative one, right? So this is how it is varying with respect to the SOC. Again, based on the paper, you will see different. There will be some variation in the result. So this is the final outcome of the simulation. So generally, this is the first thing that you report. So this is, I think, if I am correct. Um, okay, so this is the discharging curves. Okay, and so here the battery is fully charged, and this is the amount of the charge it has given, right? So it has given total, so the theoretical capacity of the battery is roughly around 1.8 mAh per centimeter square. So if I am this, so this is the first one, the red one is the, if I am discharging the battery at a really slow rate, 0.1 C, right? And the last one, when I am actually discharging the battery at the 4 C rate. You can see that theoretically the battery capacity is roughly here, but when I am discharging fast, the actual capacity of the battery is actually now become only the 50% of the actual battery, right? So the charging rate or discharging rate considerably affect the battery performance. So that's why you want to actually do the modeling. You want to understand how the battery is going to behave in a different charging discharging rate. What will be the voltage that I am going to draw? I cannot, when I am designing the battery pack, I cannot just assume that I am going to get 4.2 voltage, because as you can see, 4.2 volt I don't get. As soon as the battery start discharging, my actual voltage drops, and that is fine, but the more trickier part is that this actual voltage depend on the charging and discharging rate. No, open circuit voltage is a nonlinear function of the SOC, but the open circuit voltage was given by the previous slide. By this one, this is not the open circuit voltage, this is the actual voltage right now you are driving at a given load. This is the terminal voltage, this is not the open circuit. This is also similar, only thing is there is some kind of residual resistance. So Dr. Jain in the morning was talking about this SEI film, right? So all this molding that I told you was assuming there is no SEI interface, there is no lithium plating, right? There is no double, there is a capacitor double layer. All these phenomena I didn't discuss. But if you have try to incorporate those things, the first this SEI layer that makes it at the particle um, interface, right? So there the voltage, because there is an additional drop, voltage drop, additional voltage drop that you can see, right? And this is with respect to the Bergman coefficient. Because I have not gone into too much detail, I will not go there. The concentration of the lithium ion in the electrolyte. Okay, so this is the negative one, right, and this is the positive one, right. That what happened at the higher discharge rate, which actually lead to reduction in the capacity of the battery, right? And while digging, we ultimately settled on this particular plot. So if you see, there is a in the negative electrode, right? So if you see here, this is the curve that is drawn almost when the at this point, right? At significantly, right, when the battery is no longer functioning, right. So now if you see this blue one, right, here everywhere there is the presence of the lithium ion, right. But if you see at higher charge, that is there in the negative electrode, right. But if you see to the positive electrode, it is not there, right. So what is happening in the battery? We have seen there are so diffusion phenomena has its own speed, right. So if you're trying to draw the current too fast, right, and the diffusion, the overall uh, kinematics of the battery doesn't allow drawing of the current that fast, then what is happening? That process is slow. It's not able to actually, the lithium ions are not actually able to overcome that resistance in a way that it can actually deliver at this particular speed, right. So that's why actually you see that this way, right? Now the funny thing is, if you stop the battery, right, you stop drawing the current and you let it settle for some time, then what will happen? So right now voltage is almost 0, or let's say 2.2 or something. Well, it is not usable because the voltage has dropped at least some. It is below 2 or around 2. Right? Now, if you leave this battery for some time, now what will happen? The this lithium ions will have some time to actually go from the anode to the cathode, right? And then the battery will recover some of its potential. Right? And again, maybe you can use it for some more time if you want to use it, right? So this actually means I like this plot quite a bit. So at least to me, it explains a lot of things about that how whatever we are learning in terms of the diffusion coefficient and everything, how does actually they affect the things at the end of the day, right? I think by solving all those partial differential equations. So everything was in the. No, I have not calculated. So these all partial differential equations are hard coded in the console, and we are using the console to generate this plot. Okay. So there is another software, by the way, that is known as PyBEM. This is a Python based solver, open source solver for the lithium ion battery. This is, I think, European. There are some couple of universities which are actually leading the development of this uh, software PyBEM. It's a Python based, freely available battery solver. Okay, I have not used it personally, but I think given the kind of, I think Imperial University and Imperial and other universities are involved. You can check it out. And this is anyway not that important. Okay, so I will probably end with this slide. So again, Dr. Jain was mentioning today in morning Arrhenius equation. So in general, whatever the constant, although we have not touched upon, so this we have just seen the electrochemical modeling. We have not discussed the coupling of the electrochemical, electrochemical, with the thermal thing. But just to stress upon all the things that we have taken, diffusion coefficient, conductivity, each of these parameter are do depend on the temperature, right? So in general, if you have some explicit relationship with respect to temperature, that is well and good. But if you do not have the some special relationship, in general the by default choice is the Arrhenius equation for all the parameter in general. That is the by default one, unless until you have some extra information or something. So what I wanted to convey ki if you want to understand the thermal modeling and you want to do the other thing, even that thermal modeling, the temperature values will affect this electrochemical analysis, because that actually temperature was appearing again and again. If you see the Butler-Roemer equation, there was a term RT, there was a temperature. All these constants are also do function of the temperature, right? So things are quite connected. Electrochemical and the thermal modeling is quite connected, and yeah, so you can do the modeling, and I think time is over. I thought I will actually wind up much faster, but I had actually some extra material which I had the SEI growth modeling,